Today we begin Chapter 5. This is the last chapter that you're going to be covering in Calculus 1. It is the connection between integration and derivatives. It's pretty exciting. If you'll recall back when we first started talking about derivatives and slope, we related this to motion. So let's look at what's going on with this first graph. If our velocity is 60 miles per hour, so we're going 60 miles per hour, and we do this for 2 hours, then we would say that we have traveled, or my displacement is 60 times the 2 hours, or let's do it over here, 60 mile per hour times 2 hours would be in 120 miles. Now notice this is the area under this curve, the 60, the 2 times the 60, the length times the width, and that would get me the area. We're going to call this the area under the curve, and also we note that if we take the derivative, take the integral of velocity, we'll get displacement, and the integral of velocity gives me, we looked at this function earlier, and this was actually why they had us looking at this. The integral of velocity with respect to t gave us this displacement, and likewise I could take the derivative of displacement and get velocity. Okay, so we're focusing on the area under the curve because it's going to mean something to us, and so we're going to do a lot of skill and drill problems on approximating this area under the curve. Now this first section we won't actually be doing anything but just what really almost an elementary school kid can do, because we're going to be calculating the area under this curve, but we're not going to be doing it directly. We're just going to be approximating it. Now the first question asks you to approximate the area under this curve by just making it into two rectangles. So if I want it between 0 and 8 and I need 2 subintervals, that would mean 8 divided by 2. I would need one here at 4. So this is subinterval 1 and this is subinterval 2. And in this particular technique, I'm just taking the midpoint. Now we're going to use a couple of different techniques where we use either the left hand point or the right hand point. But in this case we're going to use the midpoint. So what I will do is I will use that height. I'll calculate the area of this first rectangle and then the area of this second rectangle, and note what the area is. This next one they want me to subdivide it into 4 intervals, so 8 divided by 4, that would mean they would be 2 in width, so each rectangle would be 2 in width, and I would get the midpoint of each one of these. You're going to see that either Excel or using your calculator table is going to be handy for this, which is what I'll be plopping up here in just a minute. So let's do this first one. Begin by subdividing it into 2 subintervals. If I'm using the midpoint, the middle in between 4 and 8 is this 6, so I will need to plug the 6 into my function. Here's my function, b equals the t squared. 6 squared, this would be 36 high. And the midpoint on this first rectangle is a 2, 2 squared is a 4. So my subinterval is, this is a 4 by 4. So a 4 by 4, this one is 16. This one is a 1, 2, 3, 4 by, and it is 36 tall, and 4 times 36, whatever that is. Hold on. Alright, so I got 144. This means the total area here is 16 plus 144, which would give me 160. And so that would be, if this is in meters per second, that means that this area would be 160 meters. My next one, I'm going to have to get all of these points that are in the middle, so I'm going to plug a 1 in here for my t. And so 1 squared, this is 1 high, this is 9, this is 25, and this would be 49. In this case, they're only 2 wide, so I would do 49 times 2. This would be 25 times 2, 9 times 2, and 1 times 2. And add all of those up. I'll write that down. Alright, I got these. And this would be 168 meters. The next one, I'm going to divide it into 8 subintervals. I'll get the point at each one of these, and it looks like this one's not going to be as nice because I'm going to have to plug in 7.5, 6.5, 5.5. I'll go ahead and get that for you with the calculator. Okay, I just had my calculator crunch these values for me. I need them from 0.5, whoops, all the way to 7.5, so I need all of these guys right in here. Just easy to get my calculator to do that for me. Notice that they're all 1 wide, which means each of these times 1, so each of these times 1 added together, and I'll see what that'll give me. Alright, adding up all of these numbers, each one times 1, because that's the width of the subinterval, this area would then be equal to 170 meters. Now let's talk about conceptually what's going on. Notice that the very first one looks to me like the area under the curve, it's missing all of this, and it's missing all of this. True, we went over a little bit, so that compensates, and that does help. But I can see that as I divide it up into more subintervals, I'm still missing out on these areas. Even though I go a little above and a little below, I'm still missing out on some. Notice how it keeps getting closer and closer to this 170. Now if I divide it up into tinier subintervals, I would get something that was even closer to the actual value. Notice that doesn't go over very much anymore. And in the textbook they carry it out to 64 subintervals. I'm not going to do that, but with 64 subintervals, so the area at 64 subintervals, they actually got 170.656. So you can see that at 8 subintervals I was pretty darn close to the area underneath that curve, and the 64 gets even closer. This first definition defines what it means to be a regular partition. I have to have a closed interval, which I had last time. I have to have a certain number of subintervals, and they tell me to make them of equal length. And this is just a little formula to let you know what size each of those subintervals would be. Ours went from 0 to 8. That made it easy. That way I knew that the length of that distance that I had to get a subinterval for, that was 8, and that's what this does here. This just takes the b minus the a on your subinterval and divide it by however many you want to make. So if I wanted to make 2 subintervals, it tells you that those, let's say I wanted n equal 2, then that just said that the length of my partition there would be 4, and we had one that was that case. Riemann sum is basically what we were doing before. It's just taking the y value times the width of that subinterval, the next y value times the width of that subinterval, and it's just writing this down formally. Now they call it a f of x star because it could be you're choosing the left endpoint or the right endpoint or the midpoint, depending on what it is that you're asked to do. This is a left Riemann sum, so this would be your f of x. You would calculate it for this point, and you don't worry about any of these. For this next rectangle, for rectangle 2, you would use this point. This is for number 2. This would be for number 1. And this would be for rectangle number 3. That would be your height. Always your width this way. And here's the height for rectangle 4. The reason I did this is because this one is a little strange. You use the height for this one for rectangle 5, and you just let that endpoint go. Same thing if you're using the right endpoint, you just let this one go. And you only calculate the heights at those particular points. And of course, we did a midpoint Riemann where we got the midpoint of each of those sections. And this is just talking about a generalized Riemann sum. So in working with Riemann sums, what I'm basically doing is just length times width, just arithmetic really. Alright, this one asked me, I've got this interval from 0 to pi over 2, and they want 6 subintervals. If you'll recall, this delta x was the pi over 2 minus the 0 over the number of subintervals. That would be 6, so each one needs to be pi over 12 in width. You'll notice that that is what happens here. Each one is pi over 12 in width. So let me just, this is pi over 12. For a left Riemann sum, I start with the left points. Sometimes it's difficult to get those left and rights, and you'll miss the whole problem because you didn't get the left or the right. So make your dots and know where they are. So for this particular rectangle, his height is 0, so you would do that area is 0 times pi over 12, and this is called showing your work, plus this next one is the width here. They're all going to be pi over 12s. Oops, supposed to be pi over 12. And then his height, should put that first, his height, so I just plug that into sine of pi over 12, and the sine of pi over 12 happens to be whatever it is, a punch on my calculator. So I want the sine of pi over 12. The next one is pi over 12 in width, and then I do sine of, and then that would be 2 pi over 12 or pi over 6 plus pi over 12 times the sine, and this would be 3 pi over 12, which is then pi over 4, plus dot 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 plus pi over 12, which is your width, times the sine of, that was 3, this is 4 pi over 12, which is then pi over 3. No need to reduce it, you could have left it as the other. 12 plus, and this would have been 4, so this one's 5, whoops, times the sine of 5 pi over 12, and I think this is 6 of them. 1, 2, 3, 4, 5, 6. Yep, that was 6 of them, and then just crunch those numbers, and you should get about 0.863. Oops, 3. Alright, so next we're going to do a right Riemann sum and just get those points. So let's move this down a little bit. Notice that these are the points that I concern myself with. In this case, it's going to be pi over 12 times the sine of pi over 12 here. So I'll write all that down. Okay, I have all of these written down. Width times my height. Notice there's 1, 2, 3, 4, 5, 6 of these subintervals. If you're off, you'll be off by 1 and your answer will still be wrong, so be careful in doing these. Notice how this area is going to be a little bit under. So that number is actually a little under what it needs to be. This area is going to be a little over what it needs to be. And I bet if you took the average of those two, it would be pretty darn close, wouldn't it? Because one's a little over, one's a little under. Next thing, they asked me to do the midpoint one. Oh no, they're not going to ask me to do the midpoint, sorry. They asked me how do these compare. I would say, I just did that One's a little over, one's a little under, and I think a good area would be just the average of those two. They did ask me to do a midpoint one. Even though they asked me to do a midpoint one, the width of all, they asked me to do it with exactly the same thing, so the width of all of these is still pi over 12. But getting the height, you have to get in the middle in between those pi overs, and those pi overs are all in the 24s, because in the middle of a 12th would then be a 24. So sometimes it's hard to think through that arithmetic. But there's 1, 2, 3, 4, 5, 6 partitions there, length times width. I get 1.003. I said that I thought I would come pretty close if you did an average of the left and the right. In this case it turns out to be 0.994, and this value is much closer to the actual, or the midpoint value, because in this midpoint when I'm going a little over and a little under, a little over and a little under, and I think this one is really close to what that actual area would be. Alright, I'm given something like this. I have to draw myself a picture. At 0, I've got a 1. At 0.5, I've got a 3. At 1, I've got a 4.5. So, whoops, needs to go a little higher. At 1.5, I have 5.5. And at 2, I have a 6. So just drawing what I think this probably looks like if it's kind of smooth. I knew that needed to be a little higher anyway. Alright, I'll fix that. I need to do the Riemann sum using the left endpoint, then do the Riemann sum using the right endpoint. So I'm going to do that in two separate. There's that one using the left endpoint. Using the left endpoint, there's this guy. Using the left endpoint, there's this one. And the left endpoint, there is this guy. I'll find the area of each of those rectangles, and this will be the area of the left. Let me make the right endpoint rectangles. Just come down here, go to this one, and down, and go here, go down. Notice how, if it's the right endpoint, I'm drawing it from the right. And so there's going to be one dot on each of them that you will ignore, either the left dot or the right end dot. So this would be the area on the right, and I'm going to write down those values. Alright, for the left, when you add all of that up, this is 1, 2, 3, 4 partitions, each one of width 0.5 times the height at the left endpoint. This would give you 7.0. The next one, using the right endpoint, would give me 9.5. Analyzing each of these, I would say that the left endpoint for this particular function is a little under what it needs to be because I've left out some of these areas. For the right endpoint, I would say this one was a little over. I would say that an average of these two would give me a better result, just because of how the function falls and it's moving upward. We can use our knowledge of summation notation to make these problems a bit easier, or not quite as, where I don't have to do the separate calculations every single time. So if I use my summation formulas, if the function itself is one that I can use this for, the Riemann sum is always that y value, whether that be the left or the right or the midpoint, times that partition value. So it can be written in a general form, and once it is, then I can use these formulas so that I don't have to do that computation for 50 subintervals, which would be a pain. Alright, so we're going to make this happen for us. I see that I have our f defined on a closed interval. It's in between 0 and 2, so there's my a and my b. and I want 50 subintervals. So k is going to go from 1 to 50. I will need to get what delta x is. Delta x in this case is going to be, if you'll remember, it's b minus a over however many subintervals that would be. So divided by that n. In our case, we have 2 minus 0 over 50, which every delta x, the width of all of our subintervals, is then 0.0. Okay, now that's going to be easier to plug into my calculator. So I'm going to plug this into my calculator using my summation features on my calculator, and I'll show you what I get and show you how to do it. Man, you see I plugged that into my calculator, and there's my area sitting right there. That is so nice. Look at that thing right there. I would say this equals 5.8416, and this is the area of the left Riemann sum. So I'm going to do this for the area of the right Riemann sum. A lot of things are very similar for the right Riemann sum, though I'm going to have this x sub k star is going to equal the a, which is 0, so I'm not writing that down this time, 0.04, which is my delta x times k. So the area on the right is going to be the sum, is k equals 1 to 50 of f of that x star, so that would be 0.04 k quantity cubed plus 1, and then that needs to be times the delta x, which is 0.04, and I'm just going to crank that out on my calculator. Okay, just punch that in on my calculator. There's the area of the right Riemann sum, and do they want me to do the midpoint? Alright, I'll do the midpoint. So I just find this x of k, plug it in for my function, and plug it into my calculator. I'll get that done. Okay, after plugging this into my calculator, this is what I get for the midpoint Riemann sum. Look, notice how it's somewhere in the middle of those two. Just plugging these into my calculator. A lot of room for sloppy mistakes here and getting the just one number wrong or plug it into the calculator wrong. Try to give me as much documentation as you can. That way I can give you as much partial credit in case you make a silly mistake. There are lots of places in here to make them. This concludes section 5.1, and it's just about length times width the whole time and calculating number of subintervals and then getting those heights. This last example in this last section shows that I can do it for subintervals of quite a large number instead of just doing it for 2 or 3 or 4. Calculator is pretty powerful on these. If you have any questions, I want to see you at the Blackboard Collaborate or email me, and thank you very much.